Dear colleagues, my presentation is about fault tolerance for real-time systems. In my presentation, I'm going to a bit extend the abilities of using verified code in the real systems. As was mentioned in the previous presentation, if there is an ability to create a system with a small core which is precisely verified and all the rest of components covered up with fault tolerance, this system might be safe. And I'm going to show you how to reach these abilities, especially for real-time systems. And I will start with some terms from classical real-time theory, because we have to be familiar with what things we are going to solve. Later on, I will cover fault-tolerant approach for real-time systems, where we have an ability to create two versions of the same software, so-called primary version and alternative version, and deal with this. And later on, I'm going to demonstrate how to model such system behavior in a real-time system. In classical real-time theory, the whole system, this whole software system, is composed from so-called tasks. For example, this is a quite common architecture of control system where we have some sort of plant, which might be a real physical process, which is supposed to be controlled by some sort of controller software, which is implemented in some sort of computer, which interacts with the real world with sensors and actuators. And inside of this computer, the software should be composed from several tasks. This task might be executed simultaneously or in a certain order. So this is quite common thing. For all, what can be a task? A task usually is treated as a basic function or function invocation. So just summarizing that real-time software is composed from several tasks. Each task might be with different behavior. Usually, if this task is periodic, it means that it executed with a certain period of time. Another sort of task is sporadic task. This task might be executed with some sort of period, but this period is not constant. So this might be a minimum period or almost unlimited period of time of this period. And so-called aperiodic tasks, which they are not executed with any period. So they are maybe just one-time execution tasks. Each execution of task is called task instance or job. So if a task is a definition of a function, then task instance or job is an invocation of this function. And each task in a real-time systems theory, in classical real-time systems theory, is accomplished with several parameters. Most commonly used parameters are execution or computation time. So if this function, if you will just invoke this function, its execution time just takes for a while. You can just estimate or measure this time, and it's called computation time and highlighted with capital C. Another very, very important parameter of task is a deadline. So deadline is a time then the task is supposed to be finished. So before the deadline, the task is supposed to be finished. If it finished after the deadline, this means deadline miss, which is supposed to be very bad for real-time systems, or even impossible or unwanted for hard real-time systems. So such kind of systems, they have to provide assurance that any task will meet a deadline. Another parameter is offset or initial phase. This is some sort of time before the task will be first invoked, starting from certain position of time. And there are lots of other parameters you can define. For example, for periodic tasks, this might be period, of course. And for sporadic tasks, this might be a minimum period, and so on. This picture briefly highlights some task parameters that might be used. So, for example, usually they defined on a timeline. You see, this is a timeline. This is the start of this line, and it goes to the right side. And this arrow up means defines some certain time, then the task will be activated. It's called an activation time. This is so-called initial phase, or just phase, when we just start the first period of periodic task, for example. And this activation time is the difference between this activation time and this time that the period was actually started. And the computation time might be estimated as a sum of time for this particular task being activated here. Here, this task, for example, was preempted by a task with another higher priority, and this is so-called deadline, the time that the task is supposed to be finished. And this is the second period of execution here, the second period of execution of the same task. T means period. What real-time systems theory, classical real-time systems theory provides us? It provides us basically several well-known scheduling algorithms that might be utilized for scheduling all of these tasks. For example, well-known scheduling algorithm is earliest deadline first, EDF. The idea of this algorithm is quite simple, to invoke the task with the closest deadline as soon as possible. Another scheduling algorithm is called rate monotonic, and this algorithm is implemented by default with code generated from Simulink. The idea of rate monotonic is also simple. It provides static priority arrangement where the priorities of tasks are arranged according to their periods. So the bigger period means the lower priority, and the shorter period means higher priority. A deadline monotonic is similar, but the priorities are arranged not according to tasks periods, they are arranged according to their deadlines. Related deadlines, I mean deadlines within their period. How can you check if you used this, for example, earliest deadline first or rate monotonic scheduling algorithm for your tasks? How can you ensure yourself if it works correctly? You have to use feasibility check. Feasibility checks are defined for well-known scheduling algorithm. For example, for EDF, this feasibility check might be defined as so-called CPU load factor. It's CPU demand or required computation time for all of these tasks within the planning period or planning cycle. And this CPU cannot go beyond 100%. Of course, for a single core computer. For rate monotonic, it might be more strict. It's supposed to be less than 69%, but this is supposed to be too pessimistic rule. In some cases, even with rate monotonic, it's possible to reach up to 100% CPU load. So to go beyond this limitation, you have to perform more exhaustive checks for your task, particular task set for your parameters. For deadline monotonic, it's more complicated because it requires to estimate response times for all tasks, for all task instances, and compare it with their related deadlines. So this technique calls response time analysis, and it requires to use some special algorithm to check this task set with all the parameters for feasibility. So what in this case we can say about fault tolerance? Because with fault tolerance we can say we can define some, there are several approaches for fault tolerance systems, and one of well-known is design diversity or recovery block approach, and this approach requires us to have two versions of the same software, primary and alternative versions. But how to implement and how to check feasibility of this approach for real-time systems? That's how I'm going to answer for this question, this section. To answer for this question, I have to define some assumptions for the solution I'm going to propose. First, all tasks are periodic and stateful. So tasks are periodic means that they are executed with certain defined period, and they are stateful. That means that these tasks are not treated as basic function invocations. or functions, because with the basic function, you have some sort of input parameters for this function, you have output parameters of this function, and these output parameters strictly depend only on these input parameters. But in the real world, these tasks they contain so-called memory blocks if you're defining them with Simulink. So they have their own internal memory. This means that output results or output data of this task will just basically depends not only on this particular input parameters. It will also depend on the previous states of this function or the previous input data as well. So this task contains its state, and I'm called or define this type of task as stateful tasks. A basic example of such task might be an implementation of digital filter, for example, because it's supposed to contain several memory blocks inside of it. The second assumption is that priorities of this task cannot be rearranged during execution. So this means that if for a certain task there was defined certain priority, this priority cannot be changed during the execution. Because if there will be an ability to provide an ability to rearrange these priorities, there's a need to define special tasks, so-called supervisor for your system, which also might be not very easy to do. So I'm going to provide this ability for quite simple designs, even for simple designs. Also, deadlines need to be taken into account because, for example, with rate monotonic scheduling, we do not take into account deadlines at all while defining this schedule. So it's better to take them into account because, for example, in the same rate monotonic scheduling, these deadlines are assumed to be equal to periods, which is not true in many cases. Also, the rest of two obvious assumptions is like the so-called not preemptive protocol is supposed to be used to just not thinking about data transfer between tasks, because in some cases this might be quite complicated problem because this might cause some deadlocks and some other unwanted effects like priority inversion and so on. But with non-preemptive protocol, this might be mitigated quite easily. And for this reason, I'm just declaring that I'm not going to go through all of these problems. I'm just providing to use this version of this solution for this particular exercise. And the last one is the solution for unicore CPU. So the only one core will be covered, but if one would like to implement it on multi-core, it means what this basically can be implemented for each core individually. So what is the approach for recovery block adaptation for this case? We have two versions of the same task, primary and alternative. What does it mean, primary version? Primary version might be a kind of debugging version. This might be optimized version. This might be a version very complex. It might be even too complex to verify it with normal amount of time or acceptable amount of time. An alternative version is so-called simplified version. It might be not so optimal, so it might provide results acceptable, but with less precision, for example. But the design complexity of this alternative version of this same task is not so big, it's not so huge, and it allows us to verify it with acceptable time. Or ensure, but it will be safe to execute it. The execution or results for both of these versions of the same task with the same input data should pass through the acceptance test. And this acceptance test provides us so-called assurance what we are going to use just one of these output results, either from primary tasks or from alternate tasks. So it allows us to decide which output we should use. The designing of acceptance test itself is not a very easy task, but it's possible. In some cases, it might be designed quite easily. Also, I have to say about the state of both of these tasks, it has to be completely independent. So if this alternative version task is invoked, it has an ability to affect all on the state only, and the same is true for primary version of task. To define the schedule for this fault-tolerant system, we have to provide some sort of scheduling algorithm. And the scheduling algorithm should provide us ability to mask all possible problems which might be caused by potential and predictable behavior of primary version of the same task. One of such unwanted behavior might be task hang. If this task instance, if the execution of specific task takes too much time, or the task instance may just basically hang, this particular situation should be mitigated somehow. And to mitigate it, we propose to use preemption and special priorities arrangement of tasks. So for this reason, we are assuming what alternative versions of tasks and acceptance tests should be executed with priorities higher than priorities for primary tasks. And also, this also provides us so-called precedence constraints, which defines what primary task should be executed before the alternative plus acceptance test, or as we assumed in the first sentence here, as it's supposed to be a recovery task. So this is supposed to be some sort of precedence constraint. And how are we going to solve this? We are going to solve this by providing a separate schedule for recovery tasks and for primary tasks. And for recovery jobs or recovery tasks, we try to use these two well-known scheduling algorithms. And I'm going to show these algorithms with the next slides. The first one is so-called EDL. EDL means earliest deadline as late as possible. As I mentioned previously, there is a well-known scheduling algorithm, earliest deadline first, and EDL is opposite to EDF. So with EDF, you have to schedule tasks as soon as it's possible, but with EDL, you have to schedule them as late as possible, but not missing their deadlines. So this probably quite related to actually how student works. Yeah. And this particular EDL schedule is composed for these task set, where the first parameter is period, the second is computation time, and the last one is a deadline. So you can see that all of these tasks are scheduled as late as possible, but without missing their deadlines. I also have to say, why is this a static algorithm? This is supposed to be static because in real life, both EDL and EDF, they assume that priorities should supposed to be rearranged dynamically. But according to our case, we are not able to rearrange priorities. That's why we are using so-called simplified version of EDL, where priorities are static. So we do not just basically use preemption in this algorithm. Another algorithm is backwards DM, or backwards deadline monotonic, which is quite related to deadline monotonic. But the idea is pretty the same. The priority arrangement is the same as with deadline monotonic, but the activation times for each task instance is adjusted so that the task will be scheduled or started its execution as late as possible, but without missing its deadline, right? So this is the schedule for backwards deadline monotonic for the same task set. A good question is how to check if these schedules are feasible, if it's possible to create such a schedule. The answer is quite simple. You have to calculate each activation time for each task instance. And if for each task instance or release time for each task instance, this formula is true, this means that this schedule for this task is feasible. TH means here least common multiple of all periods of all tasks, so-called hyperperiod or planning cycle. This is a parameter which defines the period when the old schedule starts to repeat. And for primary, but the previous 2 slides or 3 slides, they provide us information about the schedule for recovery, which are alternative tasks and acceptance tests. But what for the primary tasks? For primary tasks, we have another problem because they have to be scheduled before corresponding recovery tasks. So we have this percentage constraint, and we propose to assign deadlines for this primary task equal to corresponding release time or activation time for corresponding recovery versions of the recovery task. So this defines what these primary versions should be finished before corresponding recovery task will be activated first. And as long as we are assigning this schedule by deadlines, we are able to use deadline monotonic algorithm to schedule these primary tasks. And of course, the priority should be lowered before safety level to just ensure the preemption by the recovery versions or primary alternative versions. And here is an example of resulting schedule for a particular task set. Well, we have primary version, and here is a recovery task for this primary, and this is the second period for the same primary and recovery, and another task where we have even preemption by high priority prioritative task, and the corresponding primary version of the same task. So let me come to demonstration to say how to calculate these parameters and how to check if it works. So I created simple functions in Matlab which allows to calculate the whole schedule. I mean the whole schedule, all activation times for each task instance. And it's possible to just basically to check if they are comply to defined feasibility check and check if it's this schedule is feasible, and also additionally to check the whole schedule. I mean the composition of schedule for recovery tasks and primary task if it's feasible as well. So also to define the schedule, it's possible to determine minimal offsets for each task instance. So how to later check it with modeling software or with the real system with Simulink, for example. And for the simulation, I'm going to use Times tool. You can download for free this tool from this website, and it allows to basically just show this resulting schedule, check it for feasibility and other things. So let me just basically come to this place. So I'm going to start with my code in Simulink. So there's a definition of tasks in my application, in my program in Simulink, where I just defined 2 tasks. The period for the first one will be 30, computation time 4, deadline will be 20, and computation time for primary version will be 8. So this is computation time for recovery version. And the second task parameters, you can see it here, which is quite obvious. Then I can calculate the whole schedule according to the function I defined here. Then I can just estimate minimal release times for recovery versions of task, and which defines for me deadlines for correspondent primary versions of task, and then just basically check feasibility according to defined a feasibility check function. And the same for another scheduling algorithm. The first one was based on EDL, and the next one is based on backwards dateline monotonic. And the same is here. So basically I can just execute it and see the result. So for example, both schedules are feasible, and for example, minimum release times for our tasks, I mean recovery tasks, they are 16 for the first task and 50 for the second one. And these are the same for both of these schedules. Well, it's quite obvious because they are quite related. And what can I show next? I can show you the whole schedule, or model schedule with times tool here. So with this times tool, I defined the same task set. I mean, I have recovery versions of this task and primary versions of this tasks here, and you can basically check what all of these parameters are captured from this Matlab file and Matlab execution results. The only one thing I just put here is priority arrangement, because the recovery versions of the first task has higher priority, recovery version of task 2 has a bit lower, and primary versions has lowest priority ever. And basically I can also define here precedence constraint, because primary versions of the first task should be executed before its corresponding recovery version, and the same for the second task. I can simulate the schedule. There's no need to go beyond 60 because the planning cycle, as it was calculated here, the planning cycle is 60. So after 60 time units, the schedule will be repeated. So during the first 60 time intervals, we will have what this is the activation of first primary version of first task, and this is alternative primary version of the second task, and so on. So you can basically see how it was executed. And it's also possible to check if this schedule is feasible. So it's feasible, basically. All right, so let me get back to the presentation. So let me conclude with this. So what we can say about fault tolerance with real-time systems and implementation for it. So it's possible to design such system by taking into account special parameters of this task set and defining their alternative versions, simplified versions. And these parameters are quite simple: period, computation time, deadline, and computation time for primary version. You can calculate in Matlab with functions what I defined there, schedules and offsets for each task, I mean primary versions or alternative versions and so on, and check feasibility. Unfortunately, my feasibility check is quite pessimistic. For this reason, it's better to also check additionally and visualize the schedule in times tool and additionally check it for feasibility there again. So one can ask me, how is all of this stuff is connected with Simulink? I would say it was originally defined and designed for Simulink, because with Simulink you can define a multi-rate model where each rate will be implemented as a dedicated task. You can define rates, I mean periods or frequencies of these rates, and you can define offsets of these rates. The only one thing you cannot do there is to define your own priority arrangement. And about the priority arrangement will be the next presentation. I mean priority arrangement in Simulink, how it might be implemented. So, however, if you have any questions, just feel free to ask. And if there will be no any questions, you can postpone it for a while. So I will just leave my place to Magnus. Thank you very much.